All right, so last topic in chapter 11, section 10, normal distributions. And our learning objective is to use a normal distribution. So let's talk some definitions first. A discrete probability distribution has a finite, so means it has an ending, number of possible events or values. The binomial probability distribution you studied before is a discrete probability distribution. The events for a continuous probability distribution can be any value in an interval of real numbers. If a data set is large, the distribution of discrete values approximates a continuous distribution. So a large data set makes it more likely to behave more like a continuous distribution. All right, many common statistics such as human height, weight, or blood pressure gathered from samples in the natural world tend to have a normal distribution about their mean. A normal distribution has data that vary randomly from the mean. The graph of a normal distribution is a normal curve. And a lot of times in statistics we do talk about the normal curve. It is a classic bell-shaped curve. When you look at a normal distribution, the top of your curve hits the mean. And everything about a normal distribution is centered about your mean. So the reason we calculated standard deviations is just so we can get to normal distributions. So if you start at your mean and go to the right, one standard deviation, that makes 34% of your data points are between your mean and your first standard deviation. Then 13.5% of your data points are between your first and second standard deviation, and 2.35% of your data is between the second and the third standard deviations. With that information set, and then the same is true onto the right hand side, underneath below the mean, 34%, in between the mean and the first standard deviation, 13.5 between the first standard deviation and the second, and 2.5 between the second and third. So when you put that all together, you get 68% of the data fall within one standard deviation of the mean. That means one to the left and one to the right. Together give you 68%. 95% of data fall within two standard deviations. So if you go 13.5 plus 34 plus 34 plus 13.5, you get 95%. And then 99.7% of the data fall within 3 standard deviations of the mean. Sometimes data doesn't follow a normal distribution. So here's what a normal distribution looks like. You have symmetry about your mean right in the middle. Sometimes your data values are positively skewed, so that means your mean is more to the left. And sometimes your data values are negatively skewed, which means that data values are clustered around more to the right-hand side. So let's look at a problem where we have normally distributed data. The bar graph gives the weights of a population of female brown bears. The red curve shows how the weights are normally distributed about the mean, 115 kilograms. Approximately what percent of the female brown bears weigh between 100 and 129 kilograms. So we're going to estimate and add the percent for our intervals. So between 109, or 100 and 109, 110 and 119, and 120 and 129. So let's look on the graph. So that's here. That is here. And that is here. So we get this data point right here, which is about 23. We get this top data point here, which is about 42. And we get this data point right here, which is about 23. And we add those three items together. So that's between 100 and 129. So about 88% of female brown bears weigh between 100 and 129 kilograms. All right, so let's do this problem for the brown bears that weigh less than 120. So let's find 120. Which is here. And we want approximately what percent of female brown bears weigh less than 120. So we're going to estimate this data between 90 and 99. We're going to estimate this data and then this data. So from 110 to 119, switch to activities. 100 to 109, and from 90 to 99. Alright, so we already know that from 110 to 119 we have about 42%. From 100 to 109 we have 23%. And then from 90 to 99 we have 5. So we add those together. We get 70. One thing we have to consider is this little piece right here between 80 and 89, and that is about 1%. So our total percent is 71. So let's look at B. The standard deviation in the weights of female brown bears is about 10 kilograms. Approximately what percent of female bears have weights that are within 1.5 standard deviations of the mean? So let's clear our chart so we can get a good view. Within 1.5. So if one standard deviation is 10 kilograms and the mean is 115, so let's put that here so I remember it. We want to know within 1.5, so one standard deviation is 10 and 0.5 is 5. So we go to the left and to the right. So when you look at our previous chart, 34% are to the left or the right for one standard deviation, and then it's 13.5 for the second. So we know that this is 34 and 34%. A whole one is 13.5. But we don't have a whole amount. We only have half of a standard deviation. So half of 13.5 is 6.75. So when I add those values up, 34 plus 34 plus 6.75 plus 6.75, I end up with 81.5% that are within 1.5 standard deviation from the mean. Let's take a look at the a zoology problem and figure out how we are going to sketch a normal curve. For a population of male European eels, the mean body length of one positive and one negative standard deviation is shown below. Sketch a normal curve showing the eel lengths at 1, 2, and 3 standard deviations from the mean. So here is our mean body length. One standard deviation above is 18.5. One standard deviation below is 12.9. So let's put that in a graph. So if 15.7 is our mean, one deviation above is 18.5, one deviation below is 12.9. Doing some subtraction, you can see that it's a 12.8 deviation. All right, let's apply that for female European eels. The mean body length is 21.1, and the standard deviation is 4.7. We're going to sketch a normal curve showing eel lengths at 1, 2, and 3 standard deviations from the mean. So I'm going to pull that from here and show you what that looks like. So if our mean is at 21.1, standard deviation is 4.7, I use simple addition to get 25.8, 30.5, and 35.2. And I backtrack that and I get 16.4, 11.7, and 7.0. So now we're going to take a look at a normal distribution. So for example, the heights of adult American males are approximately normally distributed with a mean of 69.5, so here that is, and a standard deviation of 2.5. And then we do increments of 2.5. Draw a normal curve, label the mean, divide the graph into sections of standard deviation widths. Label the percentages for each section. And then when we do that, we get about 82% of adult American males are between 67 and 74.5. That's the 34, 34, and 13.5. Let's look at that same information, but now in a group of 2,000 adult American males, about how many would you expect to be taller than 6 feet? So you take your 6 feet, which is 72 inches, and you figure out the percentage. So this is 13.5, this is 2.35. Now the entire thing is 50%. So if we go 50% minus our 34, we get 0.16. So you'd expect 16% of 2,000 males to be taller than 72 inches, which is 320. All right, so let's try that for this one. The scores on an Algebra 2 final are approximately normally distributed with a mean of 150 and a standard deviation of 15. What percentage of students who took the test scored above 180? So let's draw a little curve. We know that our mean is 150. Goes right there. And we know our standard deviation is 15, so then we just add increments of 15. So that is 165. And then so then it's a 180, then it's a 195, and then we minus it. 150 minus 15 is 135, and then I got 120, and I have 105. Okay, let's draw this curve. So let's make it as symmetrical as we can. Alright. So here's our nice little standard deviation. So our data wants what percentage of the students who took the test scored above 180. So that is here. So if between here and the end is 50, then I can go 50 minus 34 minus the 13.5. And when I do the math on that, I get 2.5%. If 250 students took the final exam, approximately how many scored above 135? So if 135 is right here, I got 50% plus another 34%. Scored above 135. So then we do the math on that. 50 plus 34 is 84%. And let's double check. Let's finish out this problem. If there are 250, 84% of 250 is 210. Students. All Alright, that does it for our distribution.